this isn't going to be a slide-based presentation. This is going to be almost like a whiteboard. I'll be doing demonstrations and drawing in the image editing software I have open, just to demonstrate principles, explain some stuff. The stream is on misconceptions. There's only one common misconception that I can really think of off the top of my head, but it's a really big one. It takes a lot of examples to fully understand it. So we're going to go ahead and get started. The first thing we're going to do is prove Newton's third law. It's a neat little math proof. The claim is that for every action, there's an equal in magnitude and opposite in direction reaction. That's just Newton's third law. It's not verbatim. It's not how he wrote it in his original notebook that pretty much outlined all of classical physics. But it's good enough. You don't have to know this stuff verbatim, but you have to construct your own sentence that catches all the nuances as well as possible. The assumptions that I made is that net force is equal to mass times acceleration, and that funny looking E is just a sigma that means sum stuff up. And then the other assumption I made, or I'm going to make in the proof, is the sum of the external forces is equal to 0 if all the forces are internal. So that's pretty basic logic. If all the forces are internal, that means there's no external forces. So the sum of the forces that are external is 0 because there's no external forces in the first place. It seems pretty obvious, but it's good to lay out all your assumptions when you're doing a proof like this. So the first step is we're going to define a new quantity that you'll learn more about later. We're going to define momentum P equals mv. This is just momentum is equal to mass times velocity. And momentum is a vector quantity. It has both magnitude and direction. I'm going to draw this a little further up. And the crash course is that momentum is just an object's resistivity to a change in speed. Or, yeah, it's just a resistance to an object's change in acceleration. Or resistance to forces, rather. Really, all those are equivalent. So the first step is we're going to consider two particles that are exerting a force on one another. We're going to not make any assumption about the forces. We're just going to call them forces. The only assumption we're going to make is their direction. So we're going to assume they're exerting a force on one another. So this vector is the force from object 2. I'll draw that out bigger. The force from object 2 on object 1. Force on object 2 from object 1. And this force right here is the force from object 1 on object 2. So we're going to talk about the total momentum of the system. We're going to define that first. So the total momentum of the system, we're going to actually, I'm going to denote that as, capital P. That will be equal to the sum of the momentums in the system. And there's a distinction to make here. When we're talking about momentum being a vector quantity, we might, when we're talking about magnitudes, we would subtract the two magnitudes, right? Because the two objects are going to be moving opposite directions. But we're talking about vector quantities here. So you simply add them. And when you're doing actual number calculations, the minus sign comes in when you're talking about opposite directions. And here we're not talking about direction, or we're not specifying direction at all. So this is just going to be M1 V1 plus M2 V2. So this is just the total momentum of the system. We're going to divide both sides by the same factor, and you can do that because you're doing the same thing to both sides. So the next step is P. We're going to call that factor delta T, which is exactly what it sounds like. We're dividing both sides by a change in time. So that's M1 V1 plus M2 V2 over delta T. Okay, so the next step is we're going to talk about this momentum right here, this quantity right here. So this total quantity this total momentum quantity is going to be the total mass of the system. We'll talk about that. We'll say m sub t for total mass, times the velocity of the geometric center, or the center of mass of the system. And this is basically saying if object 2 is coming in at a faster speed than object 1, the total speed of that center as a geometric quantity is going to be moving to the left. So the center of the mass, the velocity of the center of mass, is moving to the left. So the velocity of the center of mass accounts for both the velocity of 2 and the velocity of 1, but in a way it considers it as one object. And that is over delta t is equal to m1 v1 plus m2 v2 over delta t. And the next step here is going to make it a little more obvious. So this is simply like a coefficient on the fraction, so we can move it out to the front and consider this one thing as a single fraction, right? So that's total mass times the velocity of the center of mass of the system divided by delta t. And then similarly, you can distribute this delta t to both parts of the sum. So that'll just be m1 v1 over delta t plus m2 v2 over delta t. And now we can turn these quantities into something that we know. The velocity divided by time is just going to be acceleration. So now we have the total mass times the acceleration of the center of mass is equal to m1a1 plus m2a2. So this quantity right here, the total mass and the acceleration of the center of mass, when we talk about the acceleration of the center of mass, is also just the total acceleration in a way of the system. So if we were treating it like one object, the total acceleration would also be the total, or the acceleration of the center of mass. So they're the same quantity. So I'm going to label that, or I'm going to change these two subscripts and make them the same as m SYS, that stands for system, A SYS. So mass of the system times acceleration of the system. And that's going to be equal to, let's look at the net force acting on mass 1. The net force acting on mass 1 is just going to be this F21. So this becomes F21, and this becomes F12 in a similar fashion. So, and this M subsystem, A subsystem, is going to be the sum of forces acting on the system. And now I have to make another assumption that the sum of the forces acting on any system is also equal to the sum of the forces that are external to the system, that are acting on the system. That should make at least a little logical sense. If it doesn't, just take it for what it is. The only thing that will accelerate a system is a force coming in that's external to the system. So now we have, substituting this in, we have the sum of the external forces is equal to the force from 2 acting on 1 plus the force from 1 acting on 2. And there are no forces that are external to the system. And from the same assumption right here, this means that the external forces is 0. The sum of the external forces are 0. So that means 0 is equal to F21 plus 1, 2, which then applies that the force from 1 acting on 2 is equal to the negative force of 2 acting on 1. And there's our proof. The little square means proven. So qualitatively, what that means is F1 and F2, or F12 and F21 are equal in magnitude, right? Because if we took the magnitude of both sides, like as such, if you took the magnitude of F12 and the magnitude, just applying magnitude on both sides, F21 is also equal to magnitude of -1, assuming F is in one direction, times the magnitude of F21. The magnitude of -1, or the absolute value of -1 is just 1. So the magnitude of F12 is equal to the magnitude of F21. And as you can very clearly see, if two vectors are, or if one vector is a negative of the other vector, that means they're pointing in opposite directions, right? If we have some vector pointing like this, and that vector is, I don't know, we'll call that A. I won't confuse you with that notation either. The way to construct this vector is pointing in the negative direction would just be take the negative of A. So that's that. So it's proven that for every action under these assumptions, that the net force is equal to mass times acceleration. The sum of the external forces is 0 if all forces are internal to the system. The sum of forces on a system is equal to the external, or sum of the external forces on system. And momentum is mass times velocity. Under all those assumptions, which is everything that you can see with your eyes, the law holds. For every action, there's an equal in magnitude and opposite in direction reaction. And it doesn't matter the nature of the force, because we never talked about the nature of the force. The force could be any force. It could be gravity, it could be a spring force, it could be a tension force, and it would all work out because we generalize the forces to all forces. So that's that neat little proof. I think it's nice to know. It makes a lot more conceptual sense to understand it, and it will also set you up good for momentum, which will be coming up soon. And I think momentum is personally the most tedious part of Physics 1. And if you get the concepts down, you could deal with the tedious stuff and perfect that without trouble. So the next step is we're going to be talking about third law action, or third law pairs. So we'll call that TL pairs. And they're essentially just this. They're just object 1, force being acted on object 1, object 2, force from 2 on 1, force from 1 on 2. These are just third law pairs. They say, well, if we're only looking at what object 1 is doing, object 1 is exerting a force on object 2. However, consequently, that means that there is a force on object 1 from object 2 just by that third law pair. So a third law pair is defined to be a pair that arises, or a pair of forces that arises from Newton's third law. So we're going to be looking at some common misconceptions here. And to start off, we'll consider a book on a table, a really badly drawn table. So if we're looking at the free body diagram for the book, there's a force of gravity acting downward and a normal force acting upward. And it's a common misconception to say that the force of gravity and the force normal in this situation are third law pairs. And that's not right. And the reason why it's not right is because when we're talking about third law pairs, we generalize third law pairs in this situation. And in the proof, we didn't specify a distance. We didn't specify the nature of the force. We didn't really talk about, anything. The only thing that would make this situation you have to prove it a different way as if the table was accelerating by some force, like someone pulling on it with a string. That's the only thing that would have to make us redo the proof, but it would still hold. I don't know how to do that proof, but it would hold. But we're going to look at this a little differently. So we're going to rename this normal force. We're going to rename this normal force as the force from the table acting on the book. And we're going to draw the free body diagram for the table now, for this under the table right here, or just table in general. And it'll make it a little more clear. So it's a force of gravity acting from the center of the table. And then there's a normal force here at all these contact points. There's a normal force here. But there's also a normal force acting from the book, right? A normal force is going to occur when any two objects are touching. So there's also a force normal occurring from the book. And instead of calling it Fn because it's not the same Fn right here, we're going to call this force from the book on the table. And this pair right here, or this force from the book on the table and force on the table from the book, or the force from the book on the table and the force on the table from the book, or on the book from the table, yeah. Those are equal to each other in magnitude, and they arise from Newton's third law. So those are the force pairs here. And we're talking about gravity here. For example, when we're looking at this book, the macroscopic picture is a planet, the table on the planet, and the book right here. It's a force of gravity acting on the book, but that book also pushes back on the Earth. These are the Newton's. These are the third law pairs for the book and the Earth. And in the same case, you can talk about the table and the Earth. You know, if you draw out the table on the Earth and you look at the free body diagram of the table on the Earth, you'll see that there's a normal force. The Earth is exerting on the table, and a normal force the table is exerting on the Earth, and those are third law pairs. So that's a pretty common misconception. We're also going to be talking about springs. So if we have a really badly drawn helix, and there's a hook holding the spring in, draw the dotted line. This is not working out for me. I'm really bad at drawing in 3 dimensions. So we'll consider this hook right here a box of mass M. So that's better. So this is just a spring on a ceiling. These lines are simply a fancy notation for the ceiling is rigid, meaning the ceiling's not going to move. So we don't have to worry about the ceiling moving in this situation. But when we look at the free body diagram for the box, we have a force of gravity downwards, mg, and a force from the spring. Those aren't third law pairs. And the reason why is because they're acting on the same object. We're considering the macroscopic version of the green block. So when we're trying to analyze third law pairs, we have to look as deep as the hook. So when we consider the spring, there's going to be a normal force between, there's going to be 2 normal forces between where the spring and the hook come in contact. And similarly, if we look at the the relationship between the hook and the box, what's holding them together is an adhesive force, probably glue or something like that. So the interaction would exist between the hook and the adhesive. We'll call it add. And then the adhesive and the box. So when you're thinking about third law pairs, you really have to think about what forces are holding everything together. And even the spring itself, the spring comes back together as a result of molecular interactions. Those molecules don't want to be stretched far apart from each other, so the force pushes them back inwards. So in a way, you have to really look at these as deeply as you possibly can. And you have to analyze these as deeply as you possibly can to accurately talk about a third law pair. You can't just think like, oh, there's two forces acting on each other, and those two forces are both opposite direction and equal in magnitude. In the case of the box right here, hanging from the ceiling from a spring, the two forces are opposite to each other if the box is static with respect to the ceiling, and the force of gravity is also equal to that force of the spring if it's static. So you really have to think about what's going on a deeper level. You can't just assume that they're a third law pair if they exist in an opposite direction but equal in magnitude. You really have to think about it. So when we talk about something like a box on an incline, which you'll start seeing later, box on an incline. It's definitely not perpendicular. There we go. There we go. That's a good one. Just say some unspecified angle theta. So when we're thinking about what's acting on this box, there's going to be a force of gravity, assuming no friction. There's going to be a force of gravity downwards and a normal force perpendicular to the plane, or perpendicular to the inclined plane. Quick note: I actually didn't learn this until a week ago. I thought something was a normal force because you consider it a normal force because it's like a normal thing to happen. It means normal force because it's always perpendicular to the plane, and normal means perpendicular. So that's fun. I probably should have knew that earlier, but that was never explicitly taught to me. So now you guys have it explicitly taught to you. So these are very clearly nowhere near third law pairs, right? Like that, they may be equal in magnitude, but they're not. Just by knowing how to do these problems and doing them over and over again, they're not equal in magnitude, nor are they opposite in direction. So we're gonna have to think about this a little deeper. There's two reasons why it's acting on the same object. They're not consequences of each other because they're acting on the same object, and they're not opposite in direction, nor are they equal in magnitude. So we're gonna have to analyze this a little deeper. If we draw out the components of this gravity form or this gravity vector, we think of something like this. This angle would be theta. So this would be mg cosine theta. So we're a step closer. If the box isn't leaving the plane, then they're equal in magnitude because that means there's no acceleration in the direction perpendicular to the plane. So that means they're equal to each other. And they're also opposite in direction. So we're a little closer, but not quite. We have to look at it at a deeper level. We have to think about what's going on for the inclined plane. So we draw the free body diagram for the inclined plane, which is kind of unorthodox to think about drawing a free body diagram for the plane itself. This box, well, firstly, there's a force of gravity on the plane and a normal force on the plane from the floor it's on. thinking about the interaction with the box, there's also going to be a normal force acting from the box. We're going to call that Fn2 because this one's Fn. There's a normal force acting from the box onto the plane. So put that in green again. So this and this are third law pairs, not the normal force in the gravity, not the normal force in the vertical component of gravity, or rather the parallel or perpendicular component of gravity. Those two normal forces are the third law pair. So again, we have to really think about this kind of stuff. And this concept isn't too useful for like calculations, right? Because like calculating like the force the box exerts on the plane is A, trivial if you know the normal force, because it's just the normal force again, and B, it's not really relevant to the problem, right? You'll never be analyzing that inclined plane. You'll be analyzing the box, but it helps for conceptual knowledge. Because really, if you're just going through these problems, drawing out free body diagrams, summing up the forces, and not thinking about what you're doing, it's kind of pointless. You're not really learning anything. You're learning a process, but you're not learning the behavior in nature, and that's the whole point of like talking about physics. So when we're thinking about these, it's really important to make a note in your head about the third law pairs in the system, because it'll really help you think about what's actually happening in nature in terms of how objects are macroscopically interacting with each other, and it's just a very important thing to think about, because physics is going to exist according to your eye and not according to your eye. So it's going to be the same physics. Nature is not going to behave differently. Well, not yet. You're not on an atomic scale yet, where it will behave differently. But you're not on a. You're going to be looking at the same phenomena regardless, because you're looking at it from a similar in magnitude scale. So it's important to know how to describe these systems fully, and this will become more important if you go further in physics and talk about like molecular physics, or specifically like biophysics, where you talk about the physics of interactions between molecules. Because like if I'm going to pull an extraneous example out right here, a water molecule. This is how the interaction is going to go. You can take my word for it. That's what the water is going to look like. There's going to be a third law pair here that you wouldn't really think about. They're going to attract each other that way. And there's going to be a third law pair that you'd kind of have to think about if you're thinking about interactions on a deeper molecular level. Not if you're just thinking about it macroscopically, right? Because if you have that vat of water and you're just looking at the forces on the water, you could say, oh yeah, there's gravity pointing down on the flask of water. There's a normal force from the table onto the flask of water. But if you're thinking about it on a deeper molecular level, you're going to think, yeah, there's an attraction between those water molecules that results from Newton's third law. Or a mutual attraction. There's an attraction that results from electricity, but there's a mutual attraction that results from Newton's third law. And that's why this water in front of me is liquid and not a gas, because it's close together. It's tied together by forces. And one of those is a lot more revealing about the nature of molecules and the nature of matter. And it's way more applicable to your life, in my opinion. It's a lot easier to solve problems and think about how things are going to interact with each other if you can think about it as fundamentally and deeply as possible, like on an atomic scale, like with these third law pairs, and with even as deep as the spring interacting with the hook and the hook interacting with the box, not just the spring interacting with the box. In the spring example we have right here. So this is supposed to be a Q&A, but yeah, I mean, there's not much else to it. It's the common misconception is to think of this stuff macroscopically, but really you have to zoom in at least a little bit more. And that's generally the whole point of Newton's third law. This stuff becomes, you can generalize the proof that I did right here. to like a system that does have an acceleration, like the box on the table, and someone pushing the table or pulling the table with a string. You can generalize it with an acceleration, but that would require some calculus, I imagine, to fully go out with the proof. Even then, there was a little calculus in this proof that I kind of hand-wavedly ignored. Like dividing everything by delta t wasn't the normal step for that proof. There's a calculus operation there that you have to do. But yeah, all right. So for the 5 Plus members that are watching this, after it's being uploaded, if you want to ask me a question, if you have a homework question, you can DM me. My Instagram is at jjeffries. That's my Instagram. You can follow it and ask me a question, DM me a question about your homework or just general physics, or if you just want to talk about this kind of stuff because you have a conceptual gap, you're more than welcome to. But yeah, I'm really upset that there wasn't a big show out tonight because this kind of stuff is supposed to be Q&A. But I mean, I guess that's it. For people watching this, have a good day, night, afternoon, whenever you're watching it. Alvin, if you can hear me, have a good night.